Great. Well, again, good morning or good afternoon, everyone. My name is Rami Gaddis from Logix Academy, and I'm super pleased to be joined here to continue our virtual training series sessions that we've been conducting since the beginning of April. And I'm really supportive and happy of the work that's been happening with all of our partners to support our educators across the country in getting some really neat tools and resources that you can use at home. Logix is a Canadian organization based out of Markham, Ontario. We work with schools, school districts, and parents and students at home across the country to support STEM, robotics, and coding education. We have three divisions in the company. Logix Education focuses on hardware, software, curriculum solutions, and professional development for teachers, school districts, schools, and ministries of education across the country. I know see a lot of folks from Atlantic Canada and some folks joining us now from Western Canada, which is great to see. We do have a direct-to-student program that's in school and out of school in person, but now also virtual and online. And then our consumer robotics division focuses on providing the products in retail. So working with retail partners like Best Buy, Chapters Indigo, Toys R Us, Amazon, to see all of our wonderful products available at home and at school. You might be familiar with some of our products, Dash and Dot. That's one of our most famous products across the country, used very widely, or MBot or Cody Rocky, as well as some makerspace solutions like 3D printer and laser cutters, all designed for education, and then all supported with really authentic curriculum, both learn to code and code to learn. And we focus very much on teaching computational thinking and digital literacy through a progression, through a scope of sequence aligned to international standards and provincial standards where there are for computer science from K to 12. And then at the same time, looking at these as learning resources and tools that can be used in the classroom for provincial curriculum. So we have all of our Code to Learn lesson library aligned to every single standard across the country in math, science, and tech, English language arts, social studies, etc. And of course, conducting quite a bit of professional development in person and online, as well as self-paced for educators. Really working coast to coast has been wonderful to allow us to engage with educators across the country and hear the needs of educators and see what's similar across the country, but also what's needed and specialized across the country. And so that's been a really wonderful experience for us as an organization to reflect, to learn, and to share resources and to connect teachers across the country. And in doing so, we established our Logix Educator Community, which is a free community for educators to be able to connect, collaborate together online and hear and see what other teachers in other areas of the country doing. So I encourage you, if you're interested, to just to join the community, join the conversation, hear from others, connect with others, share what you're doing. There's many discussion groups on the community for different topics, so you can join that conversation, hear, listen, learn, and share. And also want to share with you that this series is really exciting. We have a diverse number of topics brought to you. We have over 40 workshops every single week with topics from fundamentals in remote learning, platforms like Microsoft Teams, to tools like Minecraft, Flipgrid, all the way to topics like artificial intelligence, to data, to digital literacy, robotics, virtual robotics platforms, Lego, Dash's Neighborhood. You can, anything you want to learn is available for you, and it's all free and all online during this time period until the end of June, until we decide, our blended environment moving from there. And then the last thing I'll share with you today that is brand new and super exciting is that Logix Academy has launched in partnership with Microsoft and Minecraft Education in Seattle, Canadian Storytelling in Minecraft Education Edition. This is a beautiful free challenge for all individual students, teachers, or groups of students to participate in, to really give them voice and choice to share their Canadian story from across the country And what a way to launch in prior to Canada Day. So I'll actually be able to see all these beautiful stories told by students' voices and Minecraft world shared to the whole nation. So you can see all these wonderful things that students can do in Minecraft and are able to do. So I encourage you all to share it with your students and be able to create their own story, whether it's from the shipwrecks in the Atlantic Canada or in the northern coast or on an ice pond, anything that they want to talk about and share with their other students and teachers across the country, we encourage them to do so. So again, I'm delighted to be sharing all these resources with you. But today we have a very exciting workshop and session to share with you. And I'm super delighted to introduce Lynn and Cheryl, our folks from Let's Talk Science, who will be talking to us today with the topic of creative collaborators using sensors and coding to solve problems. So again, a very warm welcome to Lynn and Cheryl, and I'm super excited to learn alongside all of you today to continue to grow our discussions. So I'll turn it over to Lynn and Cheryl to walk us through today's workshop.
Thank you so much, Remy. Can you see my screen okay now?
We can indeed, yes.
Okay, and I'm just going to turn on my video. Can you see my video okay?
Not yet for your video, but oh yes,
okay.
There we are. We can see you now. Thank you.
See me okay. All right. Welcome everyone to our Let's Talk Science digital literacy webinar titled Creative Collaborators Solving Problems Using Data. And really today what we're going to focus on are unplugged and plugged activities that you can use in your classrooms to really focus on computational thinking skills and competencies. And we really like our approach in terms of using real world problems to solve. So without further ado, thank you first of all to Logix Academy for providing us this opportunity. A special thanks to Michelle, Keith, and Remy for all the support. We'll do our facilitator introductions in a few moments. So I noticed in the chat there are people from all across Canada, which is wonderful. And hopefully today you'll get some ideas that you can bring back to your classroom and share with others in their classrooms. And I always say that we learn and work best together. So if you have any suggestions or ideas going forward in the session, or you've seen something done in a different way, please feel free to offer that suggestion in the chat. And I always say, as we introduce each activity, think about how this could look in your classroom, because I noticed in the chat too, people from different grade levels. So, it might need a little bit of scaffolding down or up for your particular area. So let's get started. Let's Talk Science, as a national charitable organization, is very committed to working toward meaningful reconciliation. We believe acknowledging the traditional territory on where we work and where we live is a very small but important step in that process. It reminds us to learn more about our Indigenous peoples in all regions throughout Canada. In that spirit, I would like to acknowledge the land on which I am situated today in Newfoundland is the traditional land of the Beothuk and Mi'kmaq. I encourage each of you to reflect on where you live and where you work and how you can contribute to reconciliation in your own way. So who's in the room today? Hopefully this is intended for kindergarten to grade 6 educators, but to be honest with you, many of the activities in here can be scaffolded up easily to junior high. So, but if you do have a different role and you didn't share it already, please put it in the chat. So I'm on the right there. My name is Lynn Fitzpatrick. I've been with Let's Talk Science for about 6 years now, and very excited to be in the professional learning area as an educational specialist. I work from a home office on the south coast of Newfoundland in a small community called Marystown. So welcome everyone. I'm really happy to be with you today. So I'm going to pass it over to Cheryl to introduce herself.
Hi, everyone. My name is Cheryl Donovan-White, and I too am an education specialist in the area of professional learning with Let's Talk Science. and I work from a home office in Conception Bay South, Newfoundland and Labrador. So welcome. As Lynn said, if anytime you have any questions throughout this webinar, please don't hesitate to put the question in the chat box, and we'll do our best to answer those questions before the end of the webinar. So, who are we? Well, Let's Talk Science is a national charitable organization. Our national office is in London, Ontario, and we have two other offices, one in Calgary and one in St. John's, Newfoundland. We've been offering evidence-based STEM programs for more than 25 years, and we continue to do so. So why do we do what we do? Well, we all know that science and technology are rapidly changing the world in which we live and work and play. And we also know, and you know, that in your classrooms, and now I guess across the screen, the children that you are teaching are probably going to be, many of them are going to be working in jobs that don't even exist yet. So how can we prepare students for something that doesn't exist yet? Well, we believe by enhancing scientific literacy, by focusing on skills and competencies, and by supporting their learning through STEM education, we can help prepare them for these careers that don't yet exist, and also that will also help them to become globally engaged citizens. So what do we offer at Let's Talk Science? We have a number of things from outreach through to research and advocacy, and you can access these on our website at letstalkscience.ca, and there's an explanation for each of them and all of the different programs that are offered under each of these. So I'm going to hand it back to Lynn.
Thanks, Cheryl. We start all of our professional learning with our belief and our belief system. And we believe at Let's Talk Science, and I hope you believe this as well, that students are competent and capable of complex thinking. If we believe that, as educators, we become the co-learner and co-constructor of knowledge. Because you know yourself that knowledge-based classrooms where students are taking notes or not actively engaged in learning and just note-taking and regurgitating information can't occur anymore. That's the system that I went through in school, and I was successful in that because I was a good memorizer. But today's youth demand more from us. They want to be engaged, they want to be discovering things and learning on their own. So if we believe that statement and that we are then co-learners and co-constructors of knowledge, the best gift that you can give students is to say you don't know the answer to something. When my grandchildren were young, I used to always, when they ask questions, try to answer their questions. I don't do that anymore. I just say, I throw the question back to them. I say, what do you think? And right away then we become the co-learner with them and embark on a discovery of learning. So in this process here, what students are doing is, working on things. You created the environment for them to work on things, to try out things in the classroom. So students are saying, doing, representing. And then what our role as educators is to respond to them, to challenge them, to extend their thinking. And I always say, like, even starting with student questions, what do they want to, with a particular topic, explore further? Now, so our learning intentions for today are as follows. We want to, first of all, just do a short overview of computational thinking and the skills and competencies related to that. We're going to look at the whole idea of sensors, and the sensor that we're using, or the multiple sensors that we're using, is on a structure called a microbit, and we're going to introduce that today. We're also going to look at a real world problem and how we can incorporate coding into that problem solving using a microbit. And of course, the most important thing is engaging with you in really meaningful discussions in the chat or Q&A related to digital literacy and staying connected. So when we think about computational thinking, and I'm sure you've heard that term, well, I know in Newfoundland and Labrador, we've heard that term in the last year or so a lot. and the whole idea of coding. And Let's Talk Science did a lot of research on computational thinking just to get an idea of what researchers were saying about it and classroom teachers were saying about it. And of course, there's varied definitions of it, but we like to look at computational thinking as what students are actually doing. What are they doing when they're engaged in things, skills, and approaches of computational thinking? So let's just look at these just really briefly. Students would be, spotting and using similarities in patterns, so continuing patterns or repeating patterns. They would be breaking problems down into smaller components, an example of decomposition or the computational skill of decomposition. They'd be removing unnecessary detail from a problem and focusing on what's most important, which is the whole idea of abstraction. They'd be doing, setting up rules or a sequence of instructions to follow to do a particular thing. Like just think of coding. That is a series of instructions, and that's an example of making an algorithm. We want students being able to evaluate things, making judgments on them. And of course, the whole idea of predicting and analyzing, logic, in terms of using logic. Now, we use all those skills in different approaches. And, I'm sure you're probably doing some of these in your classroom or have seen them before, where you're designing and building things, like thinking like an engineer and creating something. And we're actually going to do an example of that today. Debugging, looking at problems in code or a sequence of things to see if there are any errors in it, and finding and fixing errors. Collaborating or working together, and that's a real skill that we want children to be able to have. So most of our activities, we encourage group work so that students are collaborating and communicating. The whole idea of perseverance, and I have 3 grandchildren, and what bothers me most, I think, when they're starting when they have a problem, is they give up easily. That they hate to fail, and I guess that's a learned thing too, but they hate to fail and they really want to give up on things. And I'm always encouraging, and that whole idea of persevering, keeping going. We want students to, if something don't work the first time, think like an engineer and try something, try another approach. And of course, the whole idea of tinkering, taking things apart, disassembling things, in other words, changing things to see what will happen. And we do all of those skills and approaches. And when we do that, we really focus on the global competencies as well. The Ministries of Education across Canada got together a number of years ago and said there are, well, I think originally it said it was 4 C's, but they've expanded it now to 6 C's, and you'll see it different ways. But the whole idea is that we want children leaving school or leaving certain grade levels being exposed to those competencies and really embracing them. In other words, I want my grandchildren to be good critical thinkers and problem solvers. And I'm sure you want your students and your own children to be like that. In other words, take things on. I want them to be creative, innovative, try new things. The third one, they're learning to learn self-awareness and self-direction. That's more true now than ever in terms of, children are not in schools in most areas. And, they have to self-pace and self-learn. So, giving them challenges that they can work on their own, and you be the guide with that in terms of that co-learner. Being able to collaborate and communicate well with others, and of course, where they are in the world in terms of global citizenship. So we're going to do an overview, first of all, of some unplugged activities, and those are ones that don't require a computing device. And then we're going to move right into our sensors and plugged activities. So I'm going to pass it to Cheryl to introduce our first activity.
Okay, our first activity is a cup stacking activity, and you will have your students working in groups of 3. One person would be the robot, the second person is the programmer, and the third person is the recorder. Now, the first person is the robot is going to be the one that wears a blindfold. Now, I know some children will not want to wear a blindfold, and that's perfectly okay. They can just close their eyes. And you'll notice on the right, there are some examples of some cup stacking patterns, and these will be available for you in the digital handout that you get. So the programmer would take one of those cards, and they would then instruct the robot how to build that particular pattern. However, the programmer can only use certain commands. Now, we have some commands here, you know, picking the cup up, putting it down, moving it forward, backwards, clockwise 90 degrees, counterclockwise 90 degrees. You could actually work with your students to come up with the commands that they would use, or you could use the ones that are here. And then, of course, your recorder is the one who's going to write down the program. And Lynn will show you a program recording sheet that you can use to do this. One of the things that you could then do is you could, between the groups, have them exchange their program and see if they can build it. So let's go to Lynn now and look at another unplugged.
Thanks, Cheryl. This one actually was suggested by an educator in one of our professional learning sessions probably a summer ago. And she said what she often does is use graph paper programming because she doesn't have a big budget for buying a lot of technology or iPads or anything. So she said it really bothered her that she really wasn't, I guess, doing a lot on directional language and things like that. So she actually introduced graph paper programming. So what students would do here is, of course, the computational skills of pattern recognition, language, sequencing, algorithms as they create a graph paper design. So all you need for this is just some grid paper, some pencils, and of course some designs to create. So working in pairs, students would program each other to draw pictures by coloring in squares on graph paper. So one person will draw as the other person actually gives the instructions. So one person programs their partner. And the programmer must use the following programming key. And I often say to people and educators too is come up with what you're going to use yourselves. Like, go forward, use a symbol for go forward. And once the students got ownership of it, I think they'll learn it better. So like you can use a symbol called pin down for actually coloring in a square instead of saying color in square. So I encourage you to do that with your classes in terms of what symbols will you use to represent your programming that you're doing. So one student would give the instructions to create a drawing, and the other student would be sketching it. And when this session is over, Cheryl will share a link to our digital handouts for all these activities that we're doing here today. And one of them is one of the handouts will be a programming sheet where you can brainstorm the available commands and include those, and then students actually write their code down. It's a great opportunity for them to see patterns and sequences coming up. The whole idea of that, algorithmic thinking and those other computational skills will come to light when you actually use the programming sheet. And what they'll often discover too is that there are repeating patterns that they can possibly put into a loop by putting, say 3 times move forward, instead of putting forward 3 times. So that's just an idea for you. In that handout too, you'll get some different designs that you can use in your classroom, and some are very simple designs and some more elaborate. There'll be a range there. So why should we use graph paper programming, and how does it relate to coding? So first of all, if they're doing those sequence of instructions, the algorithm, they are doing algorithmic thinking. So they're converting really a program into symbols. And that's what coding is. And by transforming those actions, in other words, move one square right or left or whatever, into those arrows and symbols, they are indeed coding. So don't feel like if you didn't have the budget to buy sensors and programs to use, that you can certainly do computational thinking this way. So there's lots of ways to extend the activity when doing graph paper programming. If for smaller children, I would use larger grids. You can use more complex images. You can, one real nice idea that a teacher mentioned is that once they get the instructions all wrote down on their programming sheet, pass it to another group and see if they can reconstruct the graph paper image from the instructions that they wrote down. So that's a good idea to trade programs. As I said, like putting those loops in or functions in to make the program simpler and shorter. And of course, throwing in some extra colors will add an extra layer of complexity to it. So now add a command to, instead of just saying pen down, change color and pen down. So get the students to do that with you. I'm going to pass it back to Cheryl for the activity on directional language.
Okay, so this is very much like the first activity in that you work in groups of 3. And again, you have your robot, your programmer, and your recorder. And your programmer is the one who's going to guide your robot to retrieve some kind of an item that you have placed somewhere in a room. If you can use a larger room, it's great. If you could use like the gym, for example, or a large hall or foyer in your school, that would be wonderful. And again, your recorder is the one who's going to jot down those instructions that were given to the robot. One of the things that you have to caution your robot about, though, in this activity is not to anticipate what the programmer is going to tell them, because if they can see where that object is in the room, they may want to anticipate. But they have to realize that if they're working as a computer would work, a computer can only do what it is told to do. And therefore, as the robot, they can only do what they are told to do by the programmer when they're giving them the commands. So another example of directional language is found in what a series of one of the videos in a series of videos by MakeCode. These are very short videos. They're STEM related, and they've been very well received by students grades 4 to 6, maybe grade 7. And this one's called Rubber Ducky. And when you're rubber ducking, you're actually going through code step by step, and you're giving the instructions as if it is something that doesn't think, like a computer or that robot. And instead of using directional language in terms of words, in this video, they're actually using sounds. And this is about a minute long, this video that you could show your students. Okay, so one of the really important things for any kind of activity that we do is doing a debrief, because this helps consolidate learning. So here we're going to look at a debrief of all of the activities that we just did. And what we're looking for is the skills and competencies. So we would ask, did you break the problem down into smaller steps? And obviously they would have to be able to do these. So they were using the skill of decomposition. Did they have to create a list of ordered logical steps? Well, that's a skill of algorithmic thinking. Were they looking for patterns? And Lynn talked about that. So the whole skill of pattern recognition. Did they sometimes have to find and correct bugs in their program when it didn't work the way they thought? They couldn't send a robot where they wanted them to. Well, that's the whole approach of debugging. And then, of course, they were thinking critically, collaborating, and using communication skills. So they were engaging in those global competencies. So we're now going to move into the more plugged activities. So let's talk a little bit first about how we can obtain data. And when we're obtaining data, usually, or in the past, we obtained it manually and then we recorded it, or now sometimes we still get it manually and we use a digital device to record it, or we can use devices called sensors. So what is a sensor? Well, a sensor is simply a device that detects input from its surrounding physical environment. And they're used all around the world. For example, in traffic control, if there's an area in the city where you're living and they notice that there's a lot of traffic in one area because of these sensors that have picked up this information, then might change the sequence of lighting, or they might change a bus route. In green energy, we see it all the time. You walk into the washroom at an airport and the lights come on, and you go over to wash your hands at the sink and the water comes on and the water goes off, or the hand dryer goes on and off. And those are all examples of green energy. So the different kinds of sensors are those that detect the level of light, which we call photoelectric devices, touch, Also pressure. And if we think of pressure, think of the airbag in your car in the passenger seat. I mean, it only goes on if somebody's sitting there. Detecting moisture or color, which is again looking at reflected light, and of course movement or motion that's detected by a camera. So I'm going to turn it over to Lynn now to introduce you to the microbit.
Thanks, Cheryl. Well, first of all, there are lots of different sensors that you can purchase to work in your classroom. And I think exposing children to working with sensors, you know, makes it real to them. Like a lot of times, you know, our vehicles now are all sensor driven. And, you know, you can get complacent and say, oh, well, you know, you don't need to know a big lot about it. Only the fact that it works, I suppose, or don't work sometimes. But kids are in, you know, going to be exposed to these all along, and it's wonderful to know how they actually work. So one very economical economical sensor or device that can sense things is the microbit. And it's a lot of schools here in Newfoundland and Labrador have purchased these. They're about $20 to $25. Some teachers set it up in a center if they can only afford one, and put some challenges at a center in their classroom. But I encourage you to, you know, to check that out in terms of an opportunity. Now, so the microbit, hopefully you can see this, and I can put it up in front of the camera, and the visual is actually on your screen there as well. What's really nice about the microbit is that it has 4 built-in sensors. And the sensors are, well, in various locations on the microbit. But we can sense light, sense temperature, sense speed, or there's an accelerometer there, and also a compass. So if you're looking at the microbit in terms of the structure of it, you'll see that on the side here, it has a USB port for plugging into a computer or device. You also have a reset button here and a battery adapter there, where you can actually plug in a battery supply or power supply to it, so you don't actually have to have it hooked onto the computer all the time, so it becomes mobile. And I've seen teachers use it like little projects where they're racing vehicles down a ramp, for instance, or to speed for the accelerometer. It also has 2 programmable buttons, and you'll see on the left side on your screen there, and right here, A button and a B button. So which is really a nice feature too. On A, something will happen. On B, something will happen. And then combining the 2 of them together, something else will occur. So you can program the buttons on there. The next, I think, important thing is to realize is that those 4 sensors. So first of all, I'll just talk about the light one, and Cheryl will go into a little bit more detail on it. But you'll see right on the microbit on the front there, there's a 5x5 or 25 LEDs, light emitting diodes, and they can detect light and emit light. And what's neat about them is they can display like text or images, or, you know, you can actually program each of those actual LEDs. So that's your light sensor, so it can emit light and detect light. The temperature is actually on the die surface of the microbit. You notice that when I've been holding it on the sides, like you would an old-time CD. You didn't put your hands on it. Because, of course, the temperature, first of all, the salinity of your hands might affect it, but the temperature sensor is actually on the actual CPU here. So if I lay it on the palm of my hand, then that would detect the temperature of the palm of my hand. So that's why I'm holding it by the sides there. Also, it has the accelerometer right here, so that could detect the speed of an object. And it also has, what a nice feature is, a built-in compass for directional movement. So that's the microbit. So let's get coding. And what's really nice about the microbit is that it pairs really well with a web-based coding editor called MakeCode. So this is free. So you can go into makecode.microbit.org and you'll see the URL there on your screen. And I'm new to coding. I only just started experimenting with it probably about 6 to 8 months ago in terms of starting to work on it. I showed this to my grandchildren. One is 8 and the other one is 11. And in a few minutes, they had things flashing and doing and all that, and I was still looking at the microbit. But what I found really helpful, and I think you will find helpful as well, is if you do the tutorials that's available on the MakeCode page there, on the beginning page. So when you open up makecode.microbit.org, you'll see this page, and down below there are, you know, a lot of different tutorials, like the flashing heart, or making a smiley button, or doing the rolling of the die. My actual grandson, who's only 6, actually, one of the first things that he tried was to make a stepper, and a stepper in terms of counting his steps, you know, instead of having a Fitbit, it'd be the same idea. So he programmed the microbit with a little tutorial there to actually make this into a stepper, you know, taped it onto a band on his hand, and actually had it working, you know, a 6-year-old. So, but I, older, need to spend a little bit more time doing the tutorials, and I encourage you to do that too. When you actually start a new project in MakeCode, what's great about it is that you've got a microbit simulator. So even if you cannot afford to buy the actual mobile one, there's a simulator on the left-hand side there on your screen. So any code that you develop, you can test and debug with the simulator. So, I encourage you to use that in your classrooms, even if you don't have the actual microbit. So let's look at what the screen looks like. So the simulator is on the left. So anything I program will show up there. The middle section there, you'll see it's called Blocks Menu, and you'll notice that it's all color coordinated or color coded. When you initially start makecode.microbit.org and start a new project, 2 blocks or 2 basic blocks will show up on your screen: Unstart and Forever. Depending on what program you're working on, which one you will start with, and Cheryl will explain that a little bit later, but that's your workspace. So what's neat about this is that it's a drag and drop feature. So when you find a certain code sequence you need in the blocks menu, like in the basic or input area, you just drag and drop it over. And then of course you can actually save your program and download it. And we often call that flashing it to your actual microbit. And Cheryl will go into a little bit more detail on that when we do our sensors. Now, Cheryl's going to actually introduce the actual light sensor and the program for it. But before she starts, at the end of the session, we're going to do a design and build. Think like an engineer. We're going to actually talk about doing a design and build of a seed saver with students. And in that, we want to incorporate, because we really believe coding with purpose is so important. We're actually going to code the sensor to detect light and also detect temperature in our seed saver. So that's why we're doing an activity now on a light sensor and a temperature sensor. So Cheryl, I'm going to pass it to you.
Okay, thanks, Lynn. So as Lynn explained to you, the microbit has that 5x5 array on it, and it can detect and it can also emit light. If any of you have studied physics, you know that light is measured in lumens, but our microbit is not that sophisticated. So it actually gives you a relative light intensity, 0 being the darkest and 255 being the brightest. So we are going to get started now with using our code. And as Lynn said, we're using our workspace here on MakeCode. So you'll notice when Lynn had the screen up, it had an on start and forever. And we didn't want to use the on start because that means, you know, it only is going to run the once on start, and we want now this program to continue to work for us. So we're going to leave the forever block there, and this is just a drag and drop. So all that you would have done is you would have clicked on start, dragged it over the block menu and dropped it, and it would have gone into the trash can. So what is it that we want to do? Well, we want to see a number. So where are we going to go to look for that number? So if you'll see it, it's show number, and it's also in our basic. But what do we want to show a number for? Well, it's an input. We want to see our light level. So we click on light level and we drag it and drop it on that little 0 that was there in the show number. So now what's happening is our microbit will detect the light level, and it'll also show us a number between 0 and 255 for that light level. Well, right now, that is going to happen so fast that we wouldn't be able to see it. So we want to put in a pause block, which means it'll give it enough time to scroll across the screen so that we'll be able to see what that number is. And you'll notice there's a drop-down menu there, and it's in milliseconds. You can choose one of those, or you can just type in your own number that you want to put in there. And on the left, as Lynn said, there's a simulator there, and it's showing that the light level at the time that this was done was 128, and that's the number that's going to scroll across our microbit. And it'll continue to scroll across our microbit. Now, as Lynn said, we're going to be using this in our design and build, so we want a way to make this microbit portable. So Lynn talked about flashing the code to our microbit, because right now your code is on your computer. So what are you going to need? You're going to need your microbit. You're going to need that USB cord. In the box with the microbit is also your battery pack, or your cell holder, and as well 2 AAA cells. So what you want to do first is you want to connect your microbit to your computer using your USB cable. So once you connect it, and you'll notice there's a simulation at the bottom, you want to name your program. So you'll see that it's been named Light Sensor. Then we want to save the program. And to save it, we press that little blue button right at the end of the name of our program. Once we've saved it, we want to transfer it, and it's stored as a hex file. So we want to transfer it directly to our download folder on our computer. So we'll hit the download button, and once you do that, you go into your folder, your download folder in your computer, you find the program called Light Sensor, and you're going to click on it, and you're going to drag it and drop it under devices on your computer. You'll see your microbit show up, and you'll drag that program, drop it on the microbit. And the reason we call it flashing, and it's not really obvious here, but what happens is a little amber light on your microbit will start flashing, which indicates to you that the program has been transferred to your microbit. And now you can take it, unplug it from your computer and plug it into your battery pack, making it portable, and you can use it in other activities, as Lynn talked about with the step counter that her grandson had made. So that's flashing to the microbit. If you are using a device, an iOS device, then you may use Bluetooth pairing. And if you go to this link, you'll find out how to do that. And for any of you who have used other wireless devices that you've paired them to your device, like wireless headphones, you're probably very familiar with doing that, but the instructions are there. So that's our light sensor. But now we also want to do a temperature sensor. So we're going to just remix that code. We still want it to show, what do we want it to show? We want it to show a number, but now instead of light level, we wanted it to show a temperature. And we still want that pause in there. So now we have a code, and we can flash that to our microbit as well. And we'll get a temperature reading on our microbit. So there are 4 extra challenges that are in here, and Lynn talked about pressing button A, pressing button B, or A, B. So therefore, you could really have 4 different programs on your computer, like we just on your microbit, like the one we just did where we didn't press anything. We could have A, B, and AB pressed together. So you can walk through these challenges and use these if you so wish. And again, you're going to debrief with your students what they did. And therefore, we're looking at the skills and competencies again. And Did they break it down into smaller pieces? So they were using decomposition. Your code is a series of steps. So they were using algorithmic thinking. Did they had to test and evaluate? Well, that was done for them on their simulator. And if it didn't work, then they had to go back and correct or debug their program. And of course, they were thinking critically and collaborating and using all of those kinds of competencies. So I'm going to hand it back to Lynn, and she's going to show you how to incorporate this into a design and build challenge.
Thanks, Cheryl. So this is one of our favorite things when we do workshops is designing and building. And I think engaging children in design and builds where they think like an engineer and actually plan and create and prototype things, it's so much rich learning for computational skills, for competencies and everything really. And I really believe that too often we give children answers to remember rather than problems to solve. So let's get problem solving. This is the cycle for design and build process. You'll see this represented different ways. The main thing is that it's never linear. So when we're doing a design and build, we first of all, identify a problem. Sometimes we use children's literature as a provocation, for instance, for a problem. And I'll explain that in a few minutes again as well. Then get children to brainstorm ideas. Like they'll come up with the best ideas to try to, solve a problem. And they might want to do a little bit of research with it too. Then you want them to plan what they're going to actually do to solve the problem. You might encourage, or I always encourage them to do some sketching of what they want to actually build or prototype. And what materials do they need? What plans, like planning it. Then, of course, they're going to prototype it or create it. And I always say to everyone, the most important step is the testing and evaluating stage. Remember when I spoke about that perseverance, in spite of failure, staying with it and figuring it out? Well, that's what you want children to do in a design and build. It might not work the first time. If it doesn't work the first time, what adjustments can you make so that it will work the next time? Or it might need a lot of adjustments. And we know that actually happens with engineers or anybody building anything. You try to perfect it as best you can. So you persevere and even in spite of failure the first time, you try and try again. So that should be encouraged in children to try working through it, and you challenge them in terms of how could you make that better, or what can you add to it, or what other material would be better to add to your design. And another important step, of course, is reflecting and sharing. We always get, when we do this in a group with children, we get them to actually do a gallery walk or, present their design to their classmates and test it in front of everyone too. And, I know sometimes we hate to see children if their design is going to fail, but creating that culture in your classroom that, yes, failure is celebrated because we learn more by failure. We want to try it and try it again. So what problem are we going to look at today? And really, Logix Academy is going to do a draw at the end for a gift. And we're going to actually give you this actual book because we're using this book, The Lorax, by Dr. Seuss, as a provocation today. And of course, anyone knows about the book, knows about the Lorax in the book. And unless someone like you cares a whole awful lot, nothing's going to get better. It's not. And this book really exemplifies environmental disaster. So, the Onceler and a group have come in and really, the community was beautiful with truffula trees and, fish in the ponds and, animals everywhere and plants growing everywhere. And they come in and realize that the truffula tree is good for making seeds. So they start chopping them all down. And at one point in the book, it says, and at the very moment we heard a loud whack, from outside of the field came a sickening smack of an axe on a tree. Then we heard the tree fall, the last truffula tree of all. So they've completely destroyed the environment. And so the little boy in the story is very upset, but he meets the Onceler in a tower, and the Onceler gives him something. He says, "Catch," calls the Onceler. He lets something fall. It's a truffula seed. It's the last seed of all. You're in charge of the last truffula seed, and truffula trees are what everyone needs. Plant a new truffula, treat it with care, give it clean water, and feed it fresh air. grow a forest, protected from excess that heck, then the Lorax and all his friends may come back. So I always, when I find a book that has a beautiful provocation in it, I always stop there and ask the children, can they define the problem? Like, what would be the problem in that book? And of course, the definition of the problem is, how can we protect the final truffula seed, if that's the last one of all? So the last truffula seed must be protected. And we challenge the children to use the materials provided to design and build a seed saver or seed structure that will protect the final truffula seed. You can use a real seed if you want to, like use something larger like a pumpkin seed. But what we often use is little pom-poms, all different color pom-poms, because what you'll see on the Lorax cover, of course, the truffula trees are like little pom-poms. So what do we want children to do is to build a seed saver, and what better way than to connect that actual design and build problem to a real world example. And in a location between Norway and the Arctic Circle, there's a mountain there and a cave in that mountain that's been carved out where they've actually placed a Svalbard global seed vault. It really houses 13,000 years of agricultural history in one room. So countries from all over the world have provided their seeds to this global vault, where it's protected by controlled humidity, controlled light, controlled moisture, etc. So if there is a catastrophic or something catastrophic that happens on Earth, and this, seeds are eliminated from the planet or from a country, then we have our backup seed supply in that vault. And children are really, intrigued by that. So what we're going to ask them to do is actually build their own seed saver. And these are the design criteria. Now, these are the ones that we suggested, but you can work with your class to come up with design criteria for the seed saver. So we want them to be able to use 5 to 10 different materials, a maximum of $10. And we like putting that numeracy focus on it because, limiting supplies, right? Because a lot of times if you give them too many materials to work with, they'll use them all, as you know. We want to protect the seed from extreme heat, cold, wind, and water. It should be a closed container. And remember, Cheryl went through the data collection tool of the sensor for light and the sensor for temperature. We want to actually build them into our designs. So we use the microbit. So there's just a sample materials price list. You'll get that in your digital handout too at the end. And what's great about this is that we get students to work in teams, so they collaborate and communicate. And they make those decisions on that design cycle. What materials will they use? Sketching it. And all these handouts are there to support you in doing this actual activity with your class. So here's just some sample prototypes that a group of educators that we worked with last year actually created. You'll see that it's a closed container, and they have it opened up in one section with the microbit there so that they can detect the light and temperature and actually see the display. One put a flap on it on the right-hand side there. You'll see an aluminum flap where they can actually, look at the reading on the microbit. What was really keen is that one group actually used radio signals to send the message from one microbit to the other microbit. And in other words, they could hold the microbit in their hand and leave the microbit actually inside their seed structure that allowed them to actually read it at a distance. We thought that was fantastic too. And of course, every time we do an activity, we debrief it. So we would ask the children, does your prototype solve the problem? Did it meet the design criteria that you were given? And I always say to everyone, it's not an art project. It's great if it looks nice and all that. But students should be assessed on the fact of, did it meet the criteria? Okay, so did it meet those list of 4 or 5 things that you wanted in your seed saver? And then always give them that opportunity to go back and redesign or modify the prototype. And for testing and evaluating, remember when I did the cycle, we said about testing and evaluating is so important that they get an opportunity to test to see if it will work. So what we should encourage them to put their seed saver in a really cold place or a really warm place, like a fridge or, on a windowsill where the sun is beaming in, to see actually if the inside of what they created is controlled. So, does the microbit stay on, 15 degrees, for instance? Or, is it controlling the amount of light that actually gets in there? So, encourage them to place it in different places, like a greenhouse. One educator suggested, fantastic. Put it out in a greenhouse just to see if the inside of that seed saver is controlled. And it's always great to do data collection and recording, like bringing math and science together with this STEM, of course, and getting children to actually represent their data. So if they're recording the temperature or recording the light, how are they going to represent the information, the data that they collect? In a chart or line graph, bar graph? Let them decide, and you work as a class to actually record that data. And I'm going to pass it back to Cheryl for our last little thing on cross-curricular connections.
So there are a number of cross-curricular connections in an activity like this. For example, when, in terms of literacy, you're asking questions, they're answering, they're asking questions of each other. As they're brainstorming, they're communicating their thoughts and their ideas to each other. Lynn already talked about some of the mathematical thinking connections in terms of displaying their data and collecting their data. You could also have them sort seeds and classify them and compare and contrast those seeds. And we already talked about collecting and representing data. And obviously with the visual arts, if they have to sketch their prototype and then represent it and make a model of it, then there are connections there to the visual arts as well. You can also extend the students' learning. One of the action projects that we have, well, two of them here are on the screen, Tomatosphere and Living Space. So you can get information on both of those on our website. But you could extend it by asking them, would the seed saver be different if it was on the International Space Station or on the surface of Mars or the surface of the Moon? And also looking at the conditions that are in those places, which is the connection to living space. So in wrapping up, if you have any questions, please feel free to post those in the chat, and we'll answer those the best that we can. We talked about accessing the digital handout. Here is the bit.ly link for that and the password, which is Let's Talk Science DL, Digital Literacy 2019. And there's also a link there for a survey, also a bit.ly link. And we would really appreciate it if you take a few moments to fill out that survey, because your feedback is very important to us because it helps us to improve our practice. Please stay in touch with us. And the way that you can stay in touch with us is we have a Facebook page. You can connect with us on Twitter, and we have a YouTube channel, as well as following our volunteers on Instagram. And of course, you can email us at professionallearning@letstalkscience.ca. I'd also like to thank our National Professional Learning supporters. Without them, none of this would be possible. That is the Government of Canada, Dow, Jacobs, Nova Chemicals, and SAP, and also our digital literacy supporters, who are the Government of Canada, the Canadian Space Agency, and SAP. And I've been asked to announce the winner of our draw, and that is John McLean at the Manitoba First Nations Education Resource Center. So, John, you'll be receiving a copy of the Lorax. Congratulations, and thank you.
Congratulations, John.
Thank you.
So, Cheryl,
very
I'm
much.
going to leave. Oh, go ahead.
Thank you.
Cheryl, I'm going to leave the Accessing Digital handout up on the screen for a moment or so people can jot that down. But I'd like to thank all of you for attending our webinar today on creative collaborators and getting some ideas on, I guess, how do we support computational thinking and competencies in your classroom. So look at each idea that we presented and try one or a couple of them, and I'm sure your students will be so engaged in doing science and doing these activities. So a big thank you to all of you, and a thank you to Logix Academy again for inviting Let's Talk Science along. And thank you, Cheryl, for co-facilitating today.
Oh, thank you very much.
Thank you so much, Cheryl and Lynn, for your time and wonderful information that you've been shared with us and the resources for educators to use. And congratulations to John. I know there'll probably be more questions that you can either raise your hand to ask or in the chat here. But I want to take a moment to thank Cheryl, Lynn, and acknowledge the support and partnership with Let's Talk Science in providing this opportunity for all of us.
Thank you.